Okay, now what we're really talking about here is the very last section of chapter 8. It's about unitary and Hermitian matrices. Okay, you probably haven't read forward, but maybe you have because y'all keep surprising me pleasantly. Okay, so this turns out this is a Hermitian matrix. Okay, and you can read how that's spelled, Hermition, by Hermite, I think, or Hermite. I don't know how to pronounce his name. I didn't know him very well. Okay, but it's pronounced Hermitian. This is Hermitian matrix. It's analogous to a symmetric matrix. The symmetric matrix, what's above the diagonal has to be equal to what's below the diagonal. Okay. For Hermitian matrix, what's above the diagonal has to be the complex conjugate of what's below the diagonal. Okay. So this is clearly the complex conjugate of this. That's really easy. Okay. Also, these have to be equal because we did the complex conjugate of the whole matrix, and these were complex. Then the complex conjugate would be different on the diagonal, right? So you wouldn't have the same matrix. Okay. So just a little notation for reference. Conjugate transpose. Where do I go with words again? How do I not know the word transpose here? Okay, it's automatic. Okay, so anyhow, it's conjugate transpose. I think you better take that one down. Is A star equals A transpose, which is something, well, if a matrix equals its transpose, what do you call it? That's symmetric, right? We use symmetric matrices in all the machinery symmetric matrices in chapter 7, just a couple of weeks ago. And if you remember the properties of symmetric matrices and transformations by symmetric matrices. Okay, if you have a symmetric matrix, its eigenvalues are real. It has a full set of eigenvalues. Okay, and you can diagonalize it. You just find a set of eigenvectors. Okay, and your columns of eigenvectors matrix diagonalizes it. Okay, it's the way I've said it. And no wonder I keep making mistakes. Stupid camera keeps zooming back. That's my excuse. Okay. No excuse. Okay. And it's conjugate. There's an N in the word conjugate. Not only can I remember the word transpose, I can't spell. Okay, but here we are. Okay, that's important. We say A is Hermitian. Just like a symmetric matrix, its eigenvalues are real. And distinct eigenvectors eigenvalues orthogonal eigenvectors. Now, in a 2 by 2 matrix, you are going to have distinct eigenvalues. Okay. Yeah, maybe I misspoke there. If you don't have distinct eigenvalues, especially in a bigger matrix, we might have eigenvalues of multiplicities, 2, 3, 4. Okay, whatever number. You're still going to get a set of eigenvectors that span that space. If you have an eigenvalue of multiplicity 3, which would be like you have lambda minus 2 to the 3rd power when you factor your characteristic equation. And that's not something you're going to get into in this course. So I'm not going to make you factor the characteristic equation with multiplicity 3. We don't want to distract ourselves with a lot of factoring technique, okay? But if you did, then you would have eigenvectors that span that 3-dimensional subspace. And you could Gram-Schmidt the things and get orthogonal eigenvectors. So that's worth noting. And I don't guarantee it's not something I would throw at you in a fairly simple context, but maybe not. Okay. I'll say if you don't run into it on your homework, I probably won't ask it except as an extra credit question or something. Okay. Okay, so just like a symmetric matrix, eigenvalues and real distinct eigenvectors have, or distinct eigenvalues have orthogonal eigenvectors, and the T matrix where your columns are eigenvectors diagonalizes matrix A. That is A prime equals T inverse A T. And it's like you have your space here, your space here, and this diagram. Okay. Where this thing up here is the space represented with respect to the eigenvector basis and all that stuff, right? And the matrix you get up here is diagonal, so you can do things like take powers of matrices. You gotten into Taylor series in calculus yet? You can do a Taylor series of a matrix. You do the e to the A, okay? You know that the Taylor series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. You should know the Taylor series for the sine or the cosine. That's just basic stuff. You should also be able to derive Euler's formula from those 3 things. E to the I theta equals cosine theta plus I sine theta, which saves you a lot of trouble in trigonometry and also other places, and also has very profound implications. Okay, so anyhow, you have all that. So you can do that kind of stuff with matrices, and we don't have, we're not going to get into the depth of the situation where you do that. It comes in a differential equations course. And every introductory differential equations course, in my opinion, should do this with systems of differential equations. But then it don't. So you might not even see it. But if you do see it, this is what's going on. That's how you do a function of a matrix. Okay, we do the sine of a matrix, cosine of a matrix, e to the A, if A is your matrix, and many more. Okay. Anything you can write the Taylor series for, you can do it, because the diagonalized matrix has a property that any of its powers, you just take the powers of all the numbers in the diagonal. It's really easy. Okay. So That's why this is kind of important. Also, you know, quantum mechanics is kind of really involved with summation matrices, okay? So don't know that you're going to get into heavy quantum mechanics like that, but it's kind of neat. Okay. Okay, well, back to reality here. I just wanted to invoke all this machinery from chapter 7 to show you that all you're doing is the same stuff you did in chapter 7. It's just you've got complex numbers, and it's going to work out. You're going to have real eigenvalues. So I think one of you managed to get a sign wrong or something in your calculation of your lambda for the matrix that corresponded to your numbers, okay? So as soon as I saw that, I knew there had to be something wrong. So I had to look and say, you know, I had to get my hands dirty, like I said, with the arithmetic and figure out just where it was. And it's just one sign, okay? So for this, your characteristic equation, as it happened, a couple of times after corrections, gave you real lambdas, okay? So it worked. Now, whether all your other numbers were correct, well, I didn't check everybody's numbers, okay? And unless I saw something that raised a huge red flag, okay? So anyhow, that's the context of what you're doing. And the actual calculation, well, it gets a little messy because you don't have, you know, you have square roots and stuff come out of your characteristic equation. But let's just do it. Okay, we're trying to find the eigenvalues. Eigenvalues and eigenvectors. What's the basis for eigenvalues and eigenvectors? Again, if you're working from memory and don't really focus on, you know, if you start with the equation determinant of lambda I minus A equals 0, you don't understand how that connects, okay, then you're going to tend to get lost at some point. Maybe you will, maybe you won't. That's how good your memory is. If you, and I need to pull the door, there's some more current events from the 50s and 60s. It still seems current to me. Okay, eigenvalues and eigenvectors. Okay, so you need to know from the very beginning what this means. So, and you do, but let's just write it out. Okay, so AX equals lambda X. It's an X such that when you transform it, transform X, you get a multiple of X, okay? Parallel to X, adding the same subspace, okay? All that stuff. Symmetrically and in many other ways, it's really important. Okay, so this, okay, this is familiar. You really want to, you know, if you understand this, you don't have to necessarily write it out, although on a test, it's a good idea to show me that you know the connections. So in case you screw up later, I can tell you, well, you know, you have these connections. And here's where you miss it. Okay. And this has a non-zero solution if and only if the determinant of A minus lambda I equals 0. Okay, because if the determinant of A minus lambda I is not 0, that means A minus lambda I is invertible. If the determinant of A minus lambda I is invertible, then the only solution to this is X is the trivial solution. X is the 0 vector. Okay. And that's just a little, I guess I'm going to write that out. Okay. Don't want to get too behind on time here, but so there's the whole picture. That's everything that we need to understand exactly what's going on when we calculate eigenvalues and eigenvectors. Now you notice in the context of this, I'm kind of reviewing some of the really important points of the course because we're right on the cusp of the last week. And 2 weeks from now, you're going to need to have completed your final exam. And you seem to be in good shape. It's going to take some review. Okay. Now let's get our hands dirty with this. Okay, so we want to find the eigenvalues. Meaning we want to solve, but we want to now cut to this. Now I do A minus lambda I when I do this. A lot of times you see lambda I minus A. There are fewer signs to mess up if you do it this way, and it doesn't matter. Okay. If the determinant of A minus lambda I is 0, then the determinant of lambda I minus A is 0. So in this case, A minus lambda I, well, let's say now A put some numbers in this, 3 and 6 for A and B. And the fact that this is A and this is A really has no effect because the A comes out differently when you do this part of the determinant and when you do this part of the determinant. There's really no relation. And A is the smallest number that you have in your set of numbers. And I didn't want the numbers to get too big. So I kept them as small as I could. A is A and B here and A is over here. Okay, so now we set the determinant of 3 minus lambda, 1 plus 3i, 4 minus 3i, 6 minus lambda equal to 0. And we get, well, 3 minus lambda times 6 minus lambda minus the quantity. Well, 1 plus 3i comes out, when you multiply it by itself, comes out 10. Okay, because you get 1 times 1 and negative 3i, well, 3i times negative 3i, giving you negative 9i squared here. I squared being negative 1, that gives you the positive 9, which added to the 1 you get here is 10. And this is a product of a sum of two numbers and the difference. the two numbers, okay? Comes out the difference of the two squares. So you can use your special products. Okay, well, that's got to equal 0. And check me on this, watch carefully. I think I'm getting lambda squared minus 9 lambda plus 18 minus 10. Oh man, I really didn't cheat here. I didn't set this up so that this would factor, but it's going to factor. Okay. Now I got to debate for a minute because everybody else ended up with square roots and stuff. Had to use a quadratic formula, right? I can't let myself simplify the arithmetic, because one of the things I want to do is just reinforce the complex arithmetic and how you divide complex numbers and stuff. Okay. So I'm gonna have to complicate my equation. Unintended. I change this to 7. I don't have to do too much over here. Okay. So it's going to become 7 minus I. This is going to become 7. And that's going to change my equations. Okay. Okay, now I have lambda squared minus 10 lambda plus 11. Now 11 and 1 can combine to give you 10, but a plus 11 won't give you a negative 10. Okay, so that's not going to factor. Now let's make sure that's right. That's 21. 21 minus 10 is 11. Okay, and then you got lambda squared and you got minus 10 lambda. I think that looks good. Okay, so now lambda would be negative 10 plus or minus the square root of 10 squared is 100, right? 4 times 11 is 60, is 44. So when you subtract, you get the square root of 56. I think. And you know, that's 4 times the square root of 19. That's not 19. Into 56, 14. Okay. Again, double check. That's 44. 100 minus 44. 100 minus 40, 64. Less is 56. I think that's good. Okay. So this is not as bad as what you all have. That's going to be square root of 14. The factor of 4 out and all that. Well, everybody did that right. So everybody knew the factor. Everybody did that beautifully, except for maybe a sign problem at one point. So we have this. There's our lambda. Now what do we do? Well, remember, what a minus lambda I times x equals 0. If you remember why you want that to equal 0, you're not likely to forget that that's what you want to do, right? Because it's real easy at this step to say, okay, oh, geez, what do I do next? I know there's something. Well, you go back to a lambda equals, or ax equals lambda x. Rebuild it and say, oh yeah, there's lambda. That's why you want to understand why you're doing it. Okay, so you get this. Now, your equations a minus lambda I equals 0. Well, let's just write out. We got lambda 1 equals negative 5. Do the plus first. Negative 5 plus 14. Lambda 2 is negative 5 minus the square root of 14. I don't think it's a square root. I wrote it out. There it is. Okay. Now, what's a minus lambda I? Well, here's a minus lambda I. So you just take this thing and say minus lambda I times x equals 0. And you write out 3 minus, I'm not going to write out the general. There it is. Now we use lambda 1 equals negative 5 plus the square root of 14. We get 3 minus negative 5 is 8. Minus the square root of 14. 1 plus 3i. And 1 minus 3i is going to be, no, it's 1 minus 3i. 7 minus lambda is going to be 7 minus negative 5, which is going to be 12. And then it's going to be minus the square root of 14. Okay. At this point, this translates to 2 equations. It should have identical set of solutions. So you got 8 minus the square root of 14x1 plus quantity here, 1 plus 3i x2 equals 0. And also 1 minus 3i x1 plus 12 minus the square root of 14 x2 equals 0. Now taking the first equation, let's just say that x2 is going to be negative of this over this times x1, right? Try to be careful so I don't end up with an error. And write that there. I'll do better. Okay. I'll just let x1 equal 0. Let x1 equal 1, and x2 is going to equal this, right? So we want to write this in the standard form of complex number. So we want to be able to divide by the 1 plus 3i. Okay. Now, I did show you how to do this at one point. It's fairly straightforward, just like rationalizing a denominator. So I can say that, okay, well, 8 minus the square root of 14 over 1 plus 3i equals 8 minus the square root of 14 over 1 plus 3i multiplied by 1 minus 3i over 1 minus 3i. And you see, when I multiply this, my denominator is going to end up a real number. It's going to be 10, which we're familiar with from what we did over here. Okay. So this equals 8 minus the square root of 14 minus 3i times 8 minus the square root of 14. I guess I'll do that in 2 steps. All over 10. So that's I'll write it out this way. 8 minus the square root of 14 plus I times what? It's going to be negative 24 plus 3 square root of 14, all that over 10. Now, I know that was obvious when you looked at this, but just to do the arithmetic. So this equals had to sneak my X1 in there and let myself room and anticipate it. The eigenvector would be then, no, okay. Eigenvalue is real. Okay. Had a little brain freeze there. Okay, eigenvector would be then, for example, 1. Put it out here so it's kind of centered. 8 minus the square root of 14 plus I times negative 24 plus 3 square root of 14. You probably can't read that, but it's the same expression that I had up here. Now, if I solve this, I should get something very much like that, at least a multiple of this. Okay, and if I let x1 equal 1, well, it'll come out. So up here, the solution to this one would be this. Well, if we rationalize the denominator, then hopefully we get this. 10 is 12 plus the square root of 14. The denominator comes out 120. Doesn't look like it's going to work out. We did get the 3i square root of 14. Okay. Well, at this point, I'm going to pause the video just for 1 minute and see if I can make an obvious correction in the arithmetic. Okay, it wouldn't be a bad exercise to see where I messed up, but I'm not going to take the time to reconcile this. Well, all I'm saying is that a negative 8 plus the square root of 14 is not proportional to 12 plus the square root of 14. It's the square root of 14 both times. If I'm going to get a square root of 14 here, I better get a negative 8 here, whatever the denominator is. The denominator can be different because this would still be a multiple of that, okay? And actually, maybe what I said isn't necessarily true, but anyhow, the arithmetic just doesn't work out. If the arithmetic works out, okay, what we want to do is we want to so this is basically what you're looking at, okay? It's not completely so because you want your determinant of P to equal 1. Okay, so let's just develop a little more terminology. Okay. For unitary matrix, the inverse is the conjugate transpose. Okay. For Hermitian matrix, the matrix itself equals A star. If A is Hermitian, there exists unitary matrix P such that P inverse AP is diagonal. And the process we followed is the way you find it. Just totally analogous to what we did in chapter 7. If time permits, and it might not, I'm going to go ahead and work it out with the 6 here, so we don't have all the square roots and stuff. And the arithmetic is a little less complicated. For a unitary matrix, its rows are orthogonal, meaning that the dot product of 2 rows is 0. Okay. Now, the problems you're going to have, let me just kind of put down here. I haven't worked out the exact numbers, but the problems you have in this section there's a series of problems that says determine the conjugate transpose of given matrix. Well, you flip it over the diagonal and take the conjugate, right? That's not going to challenge you. I have a couple of those just to remind you. The biggest one is, and of course, some of these matrices are not square. Your rows can be orthogonal and the matrix wouldn't be square. So unitary matrix for P inverse equals Never mind, forget it. Okay, unitary matrix has to be square because you're talking about an inverse. But well, okay. Then you have four matrices to explain why they're not unitary. Take the dot product of the rows. If they're zero, it's unitary. If not, it's okay. Then determine whether a matrix is unitary by calculating the matrix times its transpose. Because if a matrix is P, then if the inverse equals the conjugate transpose, I said the transpose, conjugate transpose, okay? Then when you multiply these P by P star, you're going to get the identity. That should be pretty obvious, okay? Then verify that they're four matrices, verify they're unitary by calculating those dot products. It all comes down to just the fact that for a unitary matrix, dot product of the rows is zero. And of course, if it's unitary, when you do the conjugate transpose, the rows become the columns, but they're the conjugates of the columns. So when you multiply a row by the conjugate of the column, you're just doing a dot product of the row with itself. Talked about that last time, it's pretty easy. Then determine whether a given matrix is Hermitian. Well, is it equal to its conjugate transpose? Again, okay. Then that's the first half of the problem set. Second half asks you to do stuff. Basically what we started doing here, okay? I wanted to start with this so that these properties would make some sense. Okay, so you got a set of, what, 6 problems where you're supposed to determine the eigenvalues. The first 4 are just 2 by 2. They probably come out a lot nicer than this one did, okay? Then there are a couple of 3 by 3s, but they're kind of simplified. There are a lot of zeros in them. Then not all those matrices have a full set of eigenvalues, okay? And of course, the ones that don't are going to be the ones that aren't Hermitian. And if they're Hermitian, you would expect a full set of distinct eigenvalues, okay? Of eigenvectors. And they probably have distinct eigenvalues, but maybe not. Then the next 4 problems ask you to calculate the eigenvectors of the ones that were, okay? So you should be able to do all that. You pretty much did it on the quiz. You might have gotten stuck at one step, but it should be familiar. The process should be familiar because you were doing it real well in chapter 7. It's just, again, you have complex numbers, and that can be, a little bit of you got to be careful. Okay, I was careful. I really thought I was going to calculate this one right, but you see, it's real easy to make a mistake, and one mistake undoes you. Then the next one says you got 4 matrices there, and I think they're pretty much the same as the matrices that you already worked on in the last 2 sets of problems, okay? And you want to find the unitary matrix that diagonalizes that, okay? So basically, I'm probably going to assign you about 4 of those, okay? And probably mostly 2 by 2s, so they work out fairly quickly, as I'll show you here in a minute, if time permits, okay? Then there's some more stuff that involves some proofs and stuff, and I'll probably give you a couple of those just to give you a little bigger perspective. Okay, let's do this again. See if it can actually work out with the matrix that I started with that I thought was too simple. So you got 3, 1 plus 3i, 1 minus 3i, 6. Determinant of A minus lambda I was again 18 and then minus 10, and it's 3 minus lambda, 6 minus lambda, okay? But no, there's your matrix, okay. It's just, I'm not gonna write down this matrix, I did it before. You're gonna have 3 minus lambda, 6 minus lambda. In your characteristic equation, it's gonna be lambda squared minus 9 lambda plus 8, which factors? So 8 and negative 1 are going to be your eigenvalues. Okay, so now this tells you that your A minus lambda I matrix, which is your 3 minus lambda, 1 plus 3i, 1 minus 3i, 6 minus lambda. I'll just write out for lambda equals lambda 1, lambda equals lambda 2. This should work. Well, for lambda 1, we get -5, 3 minus 8, and 1 plus 3i, and 1 minus 3i, and 6 minus lambda is going to be -2. And there we have it. Now, only solution happens because the only way you get a non-trivial solution is if the determinant of this matrix is 0. Because again, if the determinant of this matrix is non-zero, it's invertible. And when we invert it and multiply it by 0, 0, we get 0, 0, which doesn't help us at all. Okay. So we get these two equations, which should have compatible solutions. So from the first equation, we get x2 equals 5 over 1 plus 3i x1. And I'm going to be risky and do this in my head. I'm going to get 10 down here. And then I'm going to get 5 times 1 minus 3i, because I'm going to rationalize, multiply by 1 minus 3i over 1 minus 3i. Because of time, I'm not going to do that, because I like to take risks, because then I always screw up and then you can fix it. Okay. But 5 times 1 minus 3i is going to be 5 minus 15i. Okay. So then an eigenvector would be, I'm just looking for a place to write it, because I didn't have the room to do this one. Wrote it kind of small, but This is going to be an eigenvector. Okay. Now I simplify this. 5 over 10 is a half. Negative 15 over 10 is negative 3 halves. So it's this. Okay. From the second equation, I get wait a minute. Yeah, never mind. X2 is 1 minus 3i over 2. Well, that's 1/2 minus 3 halves I. Okay, so it works. And if you keep your wits about you and do everything carefully, it works even if you have those square roots to complicate your life. Most of the problems you have will work out this quickly. I don't guarantee all of them will because I haven't worked them all out, but they look like they're contrived to give you something that isn't too bad. So there's really no point. Again, I wanted to do that to illustrate how you do the arithmetic if you do get these square roots and stuff like that. Okay, I wanted to make sure you could do it. I'm pretty confident you could, but okay. Now the other thing is, well, we have this vector. We get another eigenvector from the lambda 2, and we don't have time to do that. I could probably do it quickly in 2 minutes, but out of board space, and I kind of leave it to you. You probably ought to do that just as an exercise to summarize things. So you're going to get 2 eigenvectors here. What's the magnitude of this eigenvector? If you dot it with its conjugate, V1 dot V1 conjugate is you're going to have 1 times 1, which is 1, okay? Then you're going to have 1/2 minus 3 halves I times 1/2 plus 3 halves I. That's 1/2 squared plus 3 halves squared, which is 1/4 plus 9/4. I'll put a little question mark on this. Okay, so that's like 14/4. Well, you normalize that by dividing by 14/4, taking 4/14 of all this. Okay, so that would give you a unit eigenvector. Okay, and then you get a unit eigenvector from the other eigenvalue. And you put those in the columns, it's going to give you an orthonormal, a unitary matrix P that you can use to the eigenvectors. Okay? Make sense? So the mechanics of the process really are much more than what you already did when I didn't even tell you any of this. Okay? But we want to pull this together and we want to understand this in terms of as much of the material we've covered in this course as possible. Kind of a capstone. There's one more capstone we'll talk about next week. A lot of you have already done the chapter. And incidentally, I don't know if I apologize to everybody, but there's way too much due today and a lot of you got it done. Okay, so this is really then kind of your last assignment, except there's one more thing I want to do with that same diminutive model. We want to calculate its eigenvectors and look at the geometry. And that's very much like section, whatever it was. where you were dealing with stochastic matrices. If you haven't done that, then you can kind of wait until Tuesday and we'll go over it if you want. But if you can do it, go ahead. Fair enough? I don't know if it's completely fair because I should have rearranged those assignments earlier, but that's it. That's what it is.